Hey guys, how's it going? Welcome to another episode of Friday Night Ferris. So smooth. This is not like an official episode. I'm home alone tonight. I thought I might as well work on stuff. Might as well stream it too. Cool. Yes, CEST does stand for Central European Summertime, which is what time it is now. Not, unfortunately, what time it shows on my stream countdown, which is stupid. But that's probably just because I haven't configured it correctly. Because I'm such a pro. Hey, Garrett Kelly, Studio C, Rep Nop, Mr. Liquid, Cold Debut. I know I said that twice, but hope I said that correctly. Dark Second. Good to see you guys. Yeah, literally just thought that I'm going to work on this anyway. Why not hang out on the stream? In particular, there's a bunch of sort of cleanup and organizational things that I want to do. I'm starting to think that there's going to be more of these library kind of things that are popping up. Maybe it's time to start moving those away. The other thing is we're not supporting or linking or running any of this standard library stuff. So other than just including these for types, which we could define ourselves, maybe we'll get rid of those. We'll see. But I think more importantly, the thing that I really want to do is work on the tooling on the PC side. In particular, I have these two separate tools. One of them's PuTTY, which will let me see the UART serial output from the system itself. And then I have this ROM loader, which will send a new ROM to the system. And you guys can't see it because I don't have like another camera set up right now. Actually, I wonder where that is. Yeah, I'm not sure. Probably up in storage. But it's resetting my FPGA every time I do that. So you would see it again if I had the UART output, but I can't connect both a writer like this and a reader like PuTTY at the same time. Not really sure why. Probably because PuTTY does both. Actually, that's something I hadn't tried. I bet if I load PuTTY and open this, and I hit a few keys. So again, I know you guys couldn't see that. Maybe I'll lift up the thing to show you. No, I can't load this. But what happened is that there's a ROM reloader on the hardware, and all it does is yeah, I can't. There it goes. Now it's in reset. And we can see the output. So what it does is it sits and just watches the UART transmitter, and when it gets 4 bytes, it expects that to be the size of the ROM that will come after. So what I did is I just hit a key 4 times, and after the 4th, then the system goes in reset, which is kind of funny. But pushing the reset on there actually does reset that, so that's pretty fun. Again, when I reset this is just the stuff from my little ROM here that's printed down here. So that's fun. Rebnop, thanks for the sub. By the way, Dark Second, thanks for the sub. I believe you subbed yesterday. Really appreciate that. And there was someone new yesterday, too, that was hanging out that also subbed, and I forgot to thank that person. But thank you so much. Really appreciate it. I think this will be a really good project to work on over the next little while, especially on the stream. I've still got a demo that I'm working on that's kind of in flight, which in my head is kind of in the same camp as this, because it's really close to hardware stuff, so that's one of the reasons why I'm inspired to work on this. But yeah. Anyway, I really want to start I'm just going to take this ROM loader thing and I'm just going to turn it into what I need it to be. One thing I haven't done is I wanted to update the software that we're using with this. Oh, also, this is just kind of random, but I was also thinking a lot about how the GPU is going to work, and that's a ways off in terms of actually implementing it. But I had some ideas. Mainly what I'm thinking, I'll just kind of share what's going on. Oh, the green screen isn't all the way over there. Screw it. 64K Logic Gates FPGA demo. That would actually be fun. I'd be into that. As long as there's a really easy way to get like video output. If that stuff's all solved, then I'd be super into that. So for the GPU, there's kind of two separate parts. There's a display part, and there's the drawing part. And then there's memory. So essentially, the display part's just going to be pulling pixels out of that whenever it needs to be able to actually show an image on screen. And then the drawing hardware is actually going to be drawing into that. It might be reading from that too if I decide to implement any kind of transparency. I'm going to hold off on that for a while just because my memory latency is bad. So I at least would want like a cache or something. Maybe I'll even implement a tiler. That'd be funny. Straight to mobile GPU territory from 10 years ago. But yeah. It's display. And then this is drawing. I don't know. I really want a cool name for the GPU. The one I'm thinking right now is Pixel Thruster, which I think just sounds ridiculous, and that's the point. So we might go with that. We'll see. But I've been kind of thinking about how this drawing part works. And in particular, it's just going to be a pipeline. So you have some kind of commands in memory somewhere. Because that's also what this needs to read is commands. So essentially, there's going to be commands in some kind of encoded format. I've been thinking about that. And then there's going to be this Pixel Blaster. Yeah, that'd be awesome. So I'm thinking about this little pipeline where essentially you have something that just sits here and reads words. And the way I want this to work, I can just kind of show what I'm thinking software-wise. I'm thinking that I'll have all these different kind of commands that you can have just as 32-bit words. And then what you would do is you'd put a bunch into memory. So you'd just have an flat array of these. And so you'd have whatever the command is plus a couple words for parameters. And what I'm thinking is that this will just go until you get a stop command. So you'd write to a particular address, which is like this register would be an address for the command list where the command list starts. And whenever you write to that, I just want the GPU to just start. And then it's just going to start pulling words out of memory at that address and increasing. And what I want it to do is I want it to go until it hits this command, this stop command. And so I'm thinking about kind of the pipe. And so there's different pieces. There's this one piece which is just going to pull words. And so what I want to do is I want to have some kind of encoding to where all the different pipeline stages will just know to stop without any kind of other interaction. So like one thing I could do is I could say the length of this list, whatever that is, like in words. But I think the solution that I want to do is instead just reserve the top bit, just for the stop bit. So if you ever get a command that just has this bit here, then just stop. So it's not even going to look at the other bits in that case, it's just going to stop. And what's really nice about that is that then you can, as soon as you write to that address, essentially all of these kick off. And actually, these ones can just always be running. It's just that they won't get commands in. So maybe I'll even do it that way. I'm not really sure because they don't really... I like that idea because then you don't even need to model idle states for these later stages. But this first one's just going to be like in an idle state. And then when you write to that, it's going to set the address in this unit. So we can call like this the word load unit. And then this is going to be the decode, the command decode. And then this is going to be execute, like just to use some existing CPU terminology. This is kind of what this would be. Or rather command fetch instead of instruction fetch, and then some basic decode. But what I'm thinking is that, so this is just going to sit there and pull words until it finds them with a stop bit, and it's just going to give it to the next stage, and that's all that this one's going to do. Then this stage is going to take in those words, and I want to use a couple more of those bits to determine whether or not that particular command is going to have more arguments. So I could just have like a big switch on whatever command it is and then read in that many arguments, but since we're going to have 32 bits to specify the command, we're definitely not going to need that many. So what I'm thinking is that some of those bits can specify, like, if we reserve a couple bits to specify how many arguments there are going to be, essentially 0 to 4, for example. Then what we can have here is we can have a 128-bit or 96-bit interface that just sends individual commands to this. So then this one's just worried about... This one doesn't worry at all about reading the commands from memory. This just worries about executing commands and whatever that means. Then this stage is just worrying about getting enough words so that it can pass the sort of somewhat decoded command to this unit, and then this one's just pulling words. And again, this one can also look for that a command in that same, look for a top bit set in that same command, just like the stage before it, and then they would just know to stop. Whereas this one's just going to keep trying to pull, but then if this doesn't feed anything, it just won't do anything. So I kind of like this design because it makes a lot of sense. Like it'd be really easy to build these from the software side, because you'd allocate some space somewhere, maybe even a growable vector, and just push commands into it. So like generating these would be really easy. And then you just write this to kick the whole thing off. And then I would have another register to just say if any of this was busy, basically. And I really like that idea. I think that's going to be a good idea. And then in terms of the features that I want this thing to have, I'm not entirely sure. I know clear is obviously going to be important. So that's probably the first one that I'm going to end up implementing. I've also thought about the frame buffer format that I want, and I'm probably going to end up, just to keep things really simple, I'm probably going to output video in 640 by 480. And the transmitter chip I have takes in full 24-bit color, which is nice, but I think to save memory bandwidth, I think I'm going to go with a 16-bit pixel format and do like 565 or something for RGB. And then clear you'd have a command which would so the other thing is that a lot of these commands will rely on internal state in the GPU, and I could either expose, like memory map all these different registers, but I think what I actually want to do is have this set register command, and then it'll have a parameter for like the register number and then the value. Again, the thing with this value is you can't have the high bit set, or else it's going to be interpreted as a stop bit from the other thing. But that's fine. So this is actually a bad example that I wrote fade bait, but this would be workable in an actual thing. So then you would have one of these to set like the clear color, which would just be 16 bits. And I also thought that maybe only some of these bits might be relevant for decoding. So then we would just use the rest for whatever. So if the argument would just fit into this command, maybe we'll just do that. So I'm not entirely sure how the encoding will work, because I'm not entirely sure which commands I want yet. But I kind of like that idea of using the top bit to be a stop bit, and then the next couple bits, maybe the 3 under that or the 2 under that or something to do like how many arguments there are, because I don't think I'm going to have commands with more than 4 arguments. If there are, then I can just have like reserved bits in those places to extend those where I might need to. Yeah, pixel thruster ISA, exactly. Now I'm getting into that name. I can have the pixel thruster, and then later if I add like a vertex processing unit, we can call that the geometry blaster or something. Nothing beats the emotion engine in the PS2, but we'll try to get close. By the way, how, comma? So yeah, the instructions are really simple, and you would just stuff those into memory. I think this will go really well. But it might also make sense that, for example, I might just keep the pattern where I always have a command word and then some additional arguments elsewhere. Bandwidth is not going to be my primary concern here, at least not with the commands, but for the pixels it definitely will be. Because essentially, I have the DDR interface I have. It actually, I blocked most of this off, but it actually does 96 word segments, or 96-bit words, because it's actually hooked up to 2 RAM chips that it accesses in parallel. So you have one that has twice as many bits as the other. It's double the size. So you essentially have a 64-bit word and a 32-bit word. And for simplicity, I just took off the upper 32-bit word part and just treated it as 128 megs of, which is a lot for this kind of system, by the way. But Vortex Explosion. Oh, I love that, you guys. Keep them coming. Polypusher, Triangle Exploder 2000, absolutely. This is great. But yeah, so it's a lot of memory, and I've just been treating it as these big 64-bit words, and then I expose that to the CPU as 32-bit words. But I think I want to give the GPU full access to the 64-bit words, so that it can do 4 pixels at a time. It would output if I did 16-bit color. I think that sounds cool, because then we're getting like 4 pixels per clock, ideally, which I think is awesome. At least if we get full pipeline utilization, and there's probably going to be some more pipelining happening in the execution unit, which we'll get to when we actually start doing commands. Maybe not, for example, for clear and some of the simpler things that I want to implement first, but for when we do polygons and stuff, it might make sense to do something more fancy. But yeah, but I also thought about maybe I can actually use those upper 32 bits as well eventually. Like, what if I have a Z buffer or something, and then I can just not use that. I cannot expose that to the CPU or have some other bit or something. I'm not entirely sure. But I kind of like that idea. No, it'd be a 28-bit machine. It'd be a 96-bit machine. So it'd be 64-bit words that you can access from the CPU as 32-bit words, but then the GPU can access it as 64-bit words. But then there's kind of, with all those same addresses, there's also actually a hidden additional 32 bits, which only the GPU could access. And maybe I could have fun with that. I'm not entirely sure. I kind of like that idea though, because we literally get those bits of data for free in a bandwidth sense, or in a bandwidth sense. We just suddenly get a bunch more data available to the GPU because we're actually accessing all 96 bits for every word anyway. I just haven't exposed any of that to the system above it because it just made more sense to kind of model it in my head as just a bunch of 32-bit words. But yeah, gotta beat the Jaguar, absolutely. So maybe we do something with that. Maybe we don't. Like, the other thing I was thinking a lot when starting this project is that I kind of wanted to have a design where portability was more of a concern, so you could kind of put this on any FPGA. I've kind of given up on that because I think that if you wanted to port a system like this to any other FPGA anyway, you'd still have to do a lot of the top level work over again, and maybe some of the timing wouldn't work on a different chip. Like, you'd have to do a lot of porting work anyway, and so I kind of would rather, if I find something fun that I can use that's on my board, I might as well just lean into it. The other thing is, if I ever wanted to make my own board, which is very far off if I ever do that, but if I ever want to do that, then again, it'd be easier if I didn't have to wire up 2 RAM chips and stuff, but we'll see. Again, I think I just want to lean into whatever I find fun, and that might be something that's cool. But that's a ways off. We still have a lot to do before we even get to this command processor. Like, I'm excited to work on this, but we've still got to get this thing actually outputting pixels. That's kind of a more important goal, because all this is kind of moot if we can't do that. I mean, I guess what I could do is I could work on it in the simulator and just pull the pixels out of the emulated memory, which would at least allow us to work on this in isolation. But I think it's more useful if we actually get to real video output from the system first and then simulate that. Because one of the things that's going to become an issue is this memory only has essentially one big port. And the display hardware and the drawing hardware and the CPU sort of bus. The CPU, and then it has a couple other peripherals out here. But essentially, that's another bus here. That will be multiplexed by all of these different things. And if we add an audio unit, that might also be pulling out a DDR. So I'm not really sure how I want to do that. It's also likely that this drawing thing will have like its own texture cache. And I might even add commands to specifically like DMA into a texture cache rather than having it figure out how that works, because I think that'd be a lot easier. So when you do texture mapper, I'll probably have some kind of limit on what size of textures you can have, and then do DMA into that memory before you actually do anything else. So I think this will be pretty cool. But yeah, I would like to get this display hardware kind of set up and kind of know what my requirements are for that so that we can work around it for everything else. And that will also be the first time where the CPU and the display hardware is actually being multiplexed on this bus. So we need to be really careful there and make sure that works. And there's a lot we can do with just the CPU and having pixels on the screen, because we can actually start implementing a software renderer as well, which is kind of how I want to. The nice thing about the shared memory architecture is that anything I want to implement in the GPU, I can prototype with the CPU, and we know kind of exactly what it's going to look like. It's going to be reading from the same memory, which is kind of cool. And I can mix hardware rendered and software rendered things always. So I can always fall back to just writing stuff with the CPU, but of course it's going to be a lot slower. So I just like that idea. So yeah, I just wanted to share my kind of thoughts on that. I think this idea is pretty good for this really simple command thing. It's just very simple stages. Obviously, the execute part is where all the complication is going to be anyway, but I think it's fun. Yeah, that'd be really cool, Dark Second. I'd be happy to help with that. I have no idea what it requires. But like if it required like a memory limit, I wouldn't mind just dropping how much memory we have, because 128 megs is a lot. I also don't know what kind of frequency that runs at, or if the device has as many logic units or as much internal RAM. I guess that's all stuff you'd have to figure out. So I think that could be fun. So yeah, not terribly complicated, but I think this will be cool. The plan for debugging later on depends on what you mean by debugging. I guess it's a pretty open question for me. In terms of like, if we start having issues where reads and writes start really messing up, then we're going to have to pull stuff into the simulator and try and isolate what happens. We'll have to see. Oh, a gig of RAM even. Wow. That's crazy. Yeah, a lot of sync bugs might creep up. I'm definitely concerned about that. We might do some lead debugging. I mean, we do technically have printf debugging. Well, we have put s debugging. We don't have printf. It's an important distinction. So, we'll just have to see. Admittedly, I don't really know. But yeah, I want to just expand this ROM loader into just kind of a general tool where it's going to watch the ROM. So as we rebuild it, that'll just be as we rebuild the ROM file, it'll just reload it for us and then also give us the output. I think that'd be nice. Let's start with that. So yeah, that's what I was going to do. I was going to update this serial port library that I used for that. So this, just in the xenowing directory, it's just ROM loader. And I think it was a while ago that I did this. And I think the library now is 3.3 is the latest version. I'm just going to update because I did also this LFSR check thing, which used that version. So we'll just go ahead and do some of this stuff. Yeah, Rust does come with a core library. I am considering running Rust on this thing with no STD and core. Especially because at one point I also prototyped a memory allocator for it. And I mean, I haven't tested it all. It just was something I played with to see how simple that could be. The Pharaoh Geo, that's great. Oh, you guys get it. You guys totally get it. Yeah, maybe we'll get Rust running on this. I think that'd be fun. But that's for another time. All right, now I'm actually enjoying doing it in C. But yeah. So one of the things that I want to kind of stop doing is this expect stuff. And just start doing, because this was actually before we had this kind of thing in Rust. And what I've just been doing with this, I know that there are libraries to make this easier, but I've been lazy. So I've just been doing this kind of pattern. What up? So I want all my expects to just be this. And I really don't care about just getting the raw debug version of the error printed out. This is fine for me. I guess this stuff kind of sucks without panics. We'll just go with it. with small tools like this, and also I don't actually want this to panic when I think about it, so I do actually want to handle some of these, because this is going to be kind of a long-running program. We'll also probably optional, or probably eventually have command line parsing for like the comport, the baud rate. Baud rate actually I want to have built in, because if you change that, it won't work. So, yeah. Also, I'm just going to start replacing stuff from this LFSR thing, because it just was so... we don't need to do that anymore either. It was just so easy to get this working. Also, I'm going to do this while we're at it. Update my addition. But not my subtraction. I'm sorry. This won't build. This is the annoying part when you have some of these errors that you just haven't covered. Let's do this. Actually, this is just, what would this be? Argument error. I guess this would be the same as expect. You know, and I think this is not gonna be input file. It's gonna be path. And I think this also works a little differently now. Here. And this is actually gonna happen anytime we want to reload the ROM, which I'm not actually gonna do initially. Let's be maybe we do want to do that. We'll move all this. Because we need to set up file watching and have this only reload when that changes. And then we'll start rewriting some of this stuff. I'm not actually that familiar with this library. I'm just throwing code together and letting the compiler tell me what I break. That's fun for me. Okay. So I might even have it where it's like I have a couple different threads where one of them does the file watching and the other one does reads. Not entirely sure. Should actually look at this library for how to use it. This is an example for receiving data, which I just took stuff from. So you can open a serial port, and I'm wondering, I think this library has, I guess that'd be duplex? Do both? Try clone. Yeah, and here we do. It's going to read and write here. I like this. We'll do this. And the reason why I'm thinking to, I guess it doesn't really matter if I thread them, does it? I don't think it does. Yeah, I'm deciding it doesn't. But actually, we might want to support some kind of user interaction as well. Hey, Mr. Network. But I don't know. We'll worry about that later. I think I'll just do. Let's do the reloads first. Or actually, we'll do reading first, and then we'll hack in the reload stuff. So in this case, I'm just gonna copy this loop here. Again, this would ideally run on like a different thread or something. Let's see this buff here. I think we can do this too. I think the example had just some uninitialized memory for the buffer. It was just reading a byte at a time. Yeah, I'm just gonna do what I have here. Read buffer. And actually, we could just do this. Like this. And do str from UTF-8 lossy. Just do that, actually. And then we may not want to flush. Yeah, that's fine. Just do this. Or actually, is it string from UTF-8 lossy? I think it is. So if we actually get an error, we do want to quit. Otherwise, we're just going to time out or whatever. So now if I just run this. Didn't like this because I didn't do argument error. Like that. It's not used. Files not used. We will use those, so leave that. And now when I reset my device, we should see print output from that. Great. That's that part done. Except we'll probably want to stuff this on a different thread, which we will do. Or actually, let's do the file watching on the other thread. It really doesn't matter. So that's what I decide. Okay, Rust file watching. We have this in our demo tool, but that was from a few years ago. I think we used this notify library, which I think everyone uses, which is great. I've got like a pre-release on this 5.0 version. Let's do the 4.0 release. I think I want to do. Because I don't want to faff with pre-release stuff, even though it's probably fine. Notify like that. So it looks like okay, so what it looks like you do with this API is you create an MPSC channel, and then you give the transmitter to a file watcher. And then it will just send you messages. I'm cool with that. but I still am probably going to have the listener for that channel on another thread because I don't know how long this is going to take. Alternatively, I could put this on the other thread. Maybe we'll just do that. Why not? We'll stick this on another thread first because it's so easy. So actually we'll do this too. Just gonna run this. Probably doesn't work, so I don't think I'm pulling in any threading stuff here. Yeah, it doesn't have thread. Should be std thread. Oh yeah, and then here, we're not handling the error because of this. This, I might just panic. Because if that happens, then we actually did have an error anyway, and then we might as well kill this. So I'm okay with that. I don't really care. Like, the OS will clean this stuff up for me. So that's good enough engineering. Yep, that still works. Great. It's so nice, by the way, how easy it is to do this stuff in Rust. And to know that this is safe enough, at least. Okay, so let's go ahead and do the watcher now. This stuff is just too easy. Go to the other thing. So yes, we need std sync psc channel. And open the port first. We'll probably need to spawn the port. Or I mean, clone it. Worry about that in a second. Yeah, and I guess we have a duration as well. That's fine. Yeah, this kind of stuff is why I use Rust. Absolutely. So this will be watcher new tx duration from sex. We can do every 1 second. Because that's up to me. I decide. Yeah, we have notify error that we need to support as well. And I'll just do this. So I want to have this here to match the other everywhere else. Some boilerplate. Don't care. Okay. Then for the watcher, say watcher.watch. You do a path. So I guess we'll do the path that contains this. Because I want this to be a file path. So then rust get file path directory. I never remember how to do this. I just look it up every time. Yeah, can you just make a path out of this? Fairly mumbly today, but that's just because I'm working hard lately. Yeah, reference to that to make our new path. Watcher.watch, and then we'll do ROM file path dot parent. Side attack, yeah. So many people are saying that now. And I might. I just might. Error found, notify error. That's fine. Yeah, we'll get there. On this way, I had these recursive mode thing here. I don't need this to be recursive, so I'm actually not gonna make it recursive. Recursive mode and non-recursive is what I want. Yeah, that's why. Argument error or path error. Yeah, ROM file path. If I do that, does that work? Is that the issue that I'm borrowing it over here? Let me actually read the output here. Temporary there. Oh yeah, probably because this. Just to make that live longer, no problem. And this I think is actually fine if I do that. Yep, and then watch looks like it gives a result. Handled. In fact, we can separate this as well. Just to clean that up a bit. Too easy, you guys. Too easy. So I think I've already made the UART programmer. What I'm doing now is extending it to also be a receiver. So I had a receiver in the form of putty, and then I have a loader just in the form of some network stuff. So now I'm just kind of putting them together in one long living program that will file watch my actual ROM file and then just update that automatically, and then also display output from the device, just for convenience, and because it's not very hard to do with this stuff. So then we'll do this looping stuff here. So what I can do here, put all this together. And then this should just be something like this. For now, we'll just do this like it says in the example to see kind of what this event looks like. And in this case, we'll actually I actually do want to break when that happens. Now this panic because it was on another thread. I don't want to do that. I'll just do something like this. That works. That's an MPSC receive error, of course. And that I actually do want to panic. Or maybe I'll add another thing for there. I'll just do that actually. Because I don't care. Do that, and then I can do this. Okay, that's the output from my device, which of course still works. Good, good. And then we'll actually do, oh yeah, I wanted to get an event. That's what I wanted to do. So let's open up another terminal where I'm going to have dev projects, xenowing, rom, make. As you can see, we got the notices. So remove. There's notice write. I don't know what the difference between that and write is. So we need to look at some API docs for that. I just noticed there's another wrapper around this if you want even less stuff, but I don't care. I'll just use this. The API documentation, I want the event. And event. Actually, we want kind, don't we? Because I think it looks like we get from an event. We can do a kind, which is public. And for the kind, we want to look at the, actually, wait a minute here. That's that 5.0 pre whatever gave me that documentation, which I didn't want actually. So let's change the version to be whatever the version was, 4 point something. Look at that documentation. Yeah, 4.0.12, that's the one. Okay, yes, we got a debounced event, it's called. You get like notice write, all that stuff. Write when a file has been written to and no events were detected for the path within the specified time frame. So chmod. So we just want write, I think. I think it's the only one we want to care about. Notice write would have been like a really quick one. So I guess we want to handle notice write or write. and then we want it to, this gives us a path buff, so we want to ideally compare these paths. I think you can compare paths. Let's see if we get a matching one with this. So we have the event, and match event. In fact, we can, that's fine. We'll do, what are these again? Debounced event, which we also want to pull in here. And we're going to have a debounced event. Notice right. And I really just want the path, actually. Or if it's a debounced event right, I want the path also. So I want, like, if let some path is this. And then here I want to do sum with the path, sum with the path. Anything else should give me none. Then I want like this, so we can actually look at the path. Don't know why I mixed that up. Okay, we'll just look here, I don't care. And then build that. Things should work more or less the same. I got to make some changes in the ROM file, which I'll do down here. Just whatever change. Make that, and then we see we got paths. So these are writes, and then we need to make sure that we watch rom.bin, which should have been the one that was specified. Let's see. Rust compare paths. Now, I don't know if it's going to tell me if they're equivalent or not. That's kind of what I'm concerned about. We could also just check the file names, actually. Just because we know that this is the right path for the file we're looking for. So I think that's probably a good way to do it. But we could also try this. If path is equal to ROM file path. I don't think this will work, but I'll try it. I'm guessing this it compiled, but I'm guessing it won't work because my gut feeling is that these paths will not be, they might be equivalent, but they won't be equal in a very simple kind of string compare sense. So if we do dot, like a file name or something. Or maybe there's, I'm going to keep looking to see if there's any way that we could check if the paths are equivalent. You want a single file? That would be even better. Good to know. I always miss stuff like that. Yeah, canonicalize, that's what I ended up finding with Googling, which is nice. Let's see, watcher new. Oh yeah, if it's just a file, that's all it is. Yeah, then that's I should just do that. Watch path is not the parent, and then we don't need to unwrap or error check this, because it's just this, and then we'll do this. And then any path we get here should be the right one. That seems much easier, doesn't it? And we did get it, which is great. So in this case, we know it's that path too, so we don't even have to do this. We just do this. These can be true, and then this will be, oops, that's funny, false. And we don't need these, which is great. And then we're gonna do the reload. Too easy, you guys, too easy. And here we're gonna want to do some error checking. If let error e is this. We might need to put this in a function. In fact, I think we do, because I think this will, yeah, I think this will not work. Yeah, because here, or does this work with a scope like this? That'd be cool. Oh, there's a method to canonicalize. That's nice. But we got away with just watching the file. It's even easier. Yeah, I don't think you can return errors like this. So let's do this. Takes the RX, and then we need the port, because that we need to clone. So let's do let receive port is port.clone. So port doesn't have clone? I thought it did. Look at notify again. I mean the serial port example. Let's try clone. Okay, and we need the actually we'll do this. P as ref path. And I don't think we have as ref in scope. We'll get that. And then we need the port. Which I need to look up the type for this. Documentation. I think it's just serial port actually. Whoops. Maybe this would have worked actually, and it was just that I had an issue with. That's funny actually. This will be reload file, ROM file path, port, and this because we need that. Report is not satisfied. What up? Actually, I think this can be as mute. You can do in a box, which is nicer. Can now borrow that because we can do this is mutable. Yeah, now we never have the path error, so we can get rid of that. We never do write. I think that's correct. Okay. That's great if that works. I do just want to try really quick here. Can I actually inline this? Just with the scope in here. For better or for worse? Does that work? Can for the type. Yeah, screw that. We'll do that. Gifted timeline. I'm glad you guys enjoy it so much. It's been a long time since I've been able to stream a couple times in a week, and I'm happy about it. Ah, that totally worked. Did you see that? Oh, that's so cool. Yeah, so what happened is I made some change in my C file here, so we can let's go ahead and do this. And then we'll make this, and we should see. There it went. So cool. So we rebuilt the ROM. Our tool noticed. I can reset this as well, and it will just output the other stuff. Whenever I make changes to this, in fact, we'll remove this now, make a change. And there it goes. I do think I want to print when it's going to reload. I want to do this, and then I want to do another print line just to clean some stuff up. Just because I can. Make some trivial change here. We'll make this. Nice. And then put len. And these shouldn't panic, by the way. These should have some kind of error. Let's just do other for this error. Just change that. I don't care. Let's do these. Oh yeah, we need to do intos on these. Thanks, fellas. Whoops, what happened there? That's funny. They just didn't line up. Whoops. Do this. And for this one, I guess we'll do since we need to specify some additional information. Just make this a little more helpful here. And then actually it's just format, because we take the string and own it. So cool. So this way, and if I delete it, so like rm rom.bin. Oh, we didn't actually get an update for that. That's okay, because we didn't update the file, so that's kind of what I wanted anyway. Did that just work, or what? I'm not sure that worked. If it did, I missed it. I'm not changing the right file now. There it goes. I think I also want to have more prints in front of this too, just to make this really kind of clear that this is happening. Hey, middle voids. I'm gonna do, it's gonna be a little obnoxious, but I think it's gonna be helpful to see this, so we're going with it. It's up to me anyway, which is fun. We'll reload this. Good. I like this. I like that it's nice and visible. I want to just remove this LFSR code. It's in Git anyway. Like this. We don't need this long string anymore, because I trust this a lot now. So cool. I feel really good about this. I'm pleased. So the only other thing that I kind of want to do is I don't want this to be called ROM loader now, because it's doing more than that. So I want to rename it. But I'm pleased. Just delete this for good measure. And we'll call this, I don't really know what to call it. Let's call it XW serial. So original, you guys. And of course, Sublime is stupid sometimes. It didn't seem to work. Actually, that's probably because I have a terminal open there. Maybe not, because I don't anyway. Call this, rename XW serial. There we go. Just run it. Yeah, colorization actually would have been a good idea. ROM Crusher 1000. Yeah, why didn't I do a stupid name? I mean, an awesome name. Yeah, colorizing would have been a good idea. How hard is that in Rust? Rust, colorize, terminal. I think it's a thing called colored, or Burnt Sushi has one. That's probably good. It's cross-platform. Looks good to me. The other thing I always hated about these, though, is that they set the color. Whereas I always would have liked that scoped. But if I can get the color, that's enough for me, because I'm only going to colorize it in this one particular case. So in this case, it looks like you make a standard stream. Is that what you do? Satisfies right color. I guess that's really what I want to look at here. Right color gives me set color, and it gives me reset. Okay, that's good enough. Yep, this is what I want then. Then I will use term color. And it didn't work because ROM file path was not specified. That's correct. So we need to cargo run rom.bin. Then things should be working. I just want to test this really quick again, even though I know this works. That, go, have this, both these open, make, and we go. Oh, this is so cool, you guys. I love this project. So many cool things. All right, let's see. We need, in here, we need to do term color. 1. I assume this isn't changing much. And then we'll remove all these stars. I do still want the extra new lines around here. That I'm okay with. Let's do let mute scd out is standard stream scd out color choice always, whatever that means. For example. And then down here, we want to do this first of all. And you know what I might do? Well, we need to figure out how we want to handle this. We'll get to that in a minute. But right now we need to import stuff. Color. And we probably need right here too, but we'll get there. CD out, and then here. Actually, we can just do this here because I'm sure we won't have issues changing this color. But just in case. Yeah, and then here, instead of print line, we do need to write line. And these all need like this. Except this one, which I think is just that. Does that work, or do we need... And we need right. This is where we need right. To have that trait here, and then all these need results that need to be used. Easy. Then, yeah, that too. This may not work with right. I think you might need this actually. Maybe not, and it's just messing up my syntax highlighting anyway, which it's definitely doing, so I'm actually gonna do that. And then stdout.reset. Now, this reset isn't going to happen with this, but I think that's probably fine. Also, I don't think this is the color I'm going to want, but we'll get to that later. We'll test it first. Yeah, I can totally just do remove rom.bin and make easier to test. Yeah, what I actually want to do, I think I want white or some kind of invert color or something. Let's look at this color spec and what that gives us. We get set foreground, set background, set bold. That's definitely what I want to do too. Intense or not? We definitely want to set intense. I think this might be all we want. That was the color spec is what we want to set that on. This I like, actually. And then what we can do is, for these cases, maybe for this one, we'll set red. I don't really like the green color, so I don't really want to do that. And then if we do like rm rom.bin and then we touch rom.bin, that should trigger an error. Or not. I thought it would. Maybe if I do it in a hex editor. Maybe it didn't work to create it, but it works to write it. Actually, and that should be something that we watch for notifications for, now that I think about it. So if we have one of these debounced events, we should watch for create. In case we remove it and then recreate it, that should also be a case where we try to reload. There we go. ROM was empty. And then do make. Nice. Maybe I do want the green. Let's try it. Let's see what it looks like. I think I do like that. Nice and clear. And the last thing I want to do is when I run this, it's not really clear to me that it's ready. It's just running. So I think I want to do this. Where here we'll print it. Connected. And away we go. I think I want something ridiculous for fun. Oh, this is so good, you guys. Cool. Oops. Pillow came off. Okay, so I think with this I'm pleased. We're done with this. That was as easy as I expected. Prepare for xenowing action. Power glove voice. Energize. All your ROM are belong to us. Okay, and I think I might want to rename this too, because I just think we can come up with a cooler name than XW Serial. So I liked your guys' suggestions earlier. ROM Crusher. So awesome. It's more than just the ROM though, right? Because it's let's just call it Blaster, which actually matches the whatever the xyling stuff was called. I don't remember. I like the idea of calling this Blaster. Of course, Sublime is dumb when you rename stuff. Stand by for action. So now I want to do xenowing Blaster engaged. Actually, I want to do git rm cached ROM bin. Really? Yeah, ROM bin. I need to go through and actually do proper git ignore on these later. I think I didn't just because I didn't know how I wanted that organized. But this is indeed what I want here. Stand by for data blast. That's great, you guys. So this I'm just resetting the device, and this is surprisingly robust, which I'm so pleased about because this used to just eat shit every time. Sick. I'm so pleased with this. I think I'm going to take a 5-minute break and get something to drink. BRB. And we're back. So where to go from here? I just pushed. That's the only thing you guys missed. So the next thing that I still want to get working is we need to talk to the transmitter chip, the HDMI transmitter chip on the board. There's quite a lot we have to do before that works. The first thing that we need to do is hook up a way to actually talk to it. So the first thing I'm going to do is go into just my memory map and kind of change some of this stuff. I also have this memory topology thing. So I think I'm going to update these docs as we go here. So right now, this is the render of it, which happens when we do make doc. And let's see, scale this down a bit. So yeah, the CPU system bus, we have the program ROM, LED interface, UART transmitter, and I haven't done any of this GPU stuff. And I'm thinking also that there's, right now, instead of the GPU display and draw, there's actually a DDR3 interface, which connects to a separate unit down here. I think there's 2 units there with how it is currently. So this might be this will change, but I want to stuff another one in here. Or I guess it's the GPU display interface, because that's kind of what we're starting already. Maybe I'll just call it the display interface, which is different than the graphics processing unit. And the way they're going to be implemented is they're going to be completely separate anyway. So it's just that we're going to need this arbiter. But initially, the display is just going to have some kind of memory mapped I2C bus, which right now I'm just going to set it up so I can bit bang it, because that's going to make it a lot easier to do initially. So then it'll just be the display interface, and then that hooks up to whatever display hardware there is down here. Because I've done a pretty good job of like this also is not correct. It doesn't talk to the UART transmitter. It talks to the UART transmitter interface, which then talks to the UART transmitter. So we can actually update some of that too. The other thing, I keep seeing this says indented. This should say intended. Good time to finally fix that. But yeah, so I've mapped off a bunch of the memory map here. So I've decided these not highest 4 bits, but the 4 bits below that. So you get 0, 1, 2, 3. These determine kind of the main regions. So you have ROM, system registers, and the DDR3 memory, and then everything else, as it says here, they have undefined behavior. But I actually, to avoid like stalls, I do actually do dummy writes or return dummy values when you read out of these. I might actually change that and just have the CPU stall forever when that happens, because you shouldn't be doing that anyway, and it simplifies our hardware design. In fact, I might do that right now, actually. Just because that's kind of a nice thing that we want to catch. Like, we don't want writes happening there, or reads, so might as well just disallow it. I think that's in the RTL here. Let me do a couple things. Just leave this running. Why not? What happened here? Oh yeah, I need to have this terminal have min-gw in it, so that we can actually build the variolator stuff. I don't know if I said that yesterday, Dark Second, by the way, but congrats on getting variolator set up. Oops. That's really cool. Make. This should just work. Yeah, we couldn't. It couldn't make this document because we have it open. That's fun. This make will also do all the docs. So if I do make test, for example, this will build and then run the simulator. And so from there, we can also go ahead and open the simulator view, which I think I'm just going to open, what's it called? GTK wave. And open up the xenowing test trace. And I don't have anything in here. Also, this says nanoseconds for the timescale, which is just bullshit, I think. In this trace. Maybe it's correct. I don't remember. But let's say let's do CPU control state, which I think ends up being this node, just the way I have this set up. Actually, we can do all the enables for the different stages. So this is instruction fetch. It's going and fetching a bunch of instructions. After that, it does decode, and then it does register wait, which actually it doesn't export a signal for, so we'll just have an empty one there, and then it does execute, and then mem, and then write back. Oh, it does have a reg wait enable. Good. I'll do this. So these are different. This is the CPU as it goes through different states. So if we open this up, we see this cascades. This is because I put that in the wrong order. So it just cascades through different states. Nice and easy. Yeah, I really need to end up. I really need to switch to WSL, but I just haven't sat down and moved everything. Honestly, I'll probably end up making the switch finally the next time I install Windows, because I'm just so lazy with that stuff. The thing is, I just don't care enough. But yeah, that's awesome, Dark Second. I still got to move my ALU to Python, but I don't want to do that today. I don't feel like it. But yeah, so we can see that it cascades a bunch of these. And what we can do is I just want to make the hardware change that I want to make, actually. In fact, what we can do first is open up the ROM. And I actually want to change the assembler code because it's going to be easier if I just do that. So if we go into the ROM, we can do rom.s. Whoops, not .mif. That's the preparing the file for Quartus. So I'm going to leave this running. Well, actually, that doesn't matter because we're going to be looking at the simulation anyway. But instead of jumping into this actual code, goes and touches a bunch of memory, I want this load to happen right away. So what I want to do is I'm going to do li, which I believe will generate the right instructions to load a particular immediate. So let's do this first address within this like illegal region. And then we will do a load, which is load word. Oh yeah, we need to do like x1, for example. We can do x2, 0, x1. This will try and load a word from this address range. And if we build that, which in this case is just make test, so that'll build. Actually, that's not just make test because it changes the ROM, which I need to have on this. So we'll make that, and then we'll do make test. And then we got the new trace. So if I refresh this, what? That's not what I expected. You can see we got through one instruction and then didn't finish this one. And it looks like what happened is in the write back stage, it probably issued a memory read and it never gets this data back. I'm guessing that's what's happening. Now, I think this is actually a bug because I think this should have worked. And in fact, what we can do is we can look at the top level CPU thing here. We can look at there's a lot of stuff here. We can look at the xenowing actually and do the system bus. So this is the system bus address. And actually, let's take that out of the CPU. There should be a or system bus 0 maybe. Maybe we do just get these word addresses. That's fine. Let's go ahead and pull these off of here then. The CPU should have for the system bus, because we want to see write data. No, we want to see read request and then the bus address, which is the address because it uses both. And this 4,000 here shifted. Yeah, it's different because these are the instruction fetches. Is what we see here. because it gets shifted. So this should be the right address. So it loads this instruction and then loads the next instruction here, just that instruction fetch, and then here it issues the write, and we can see if we say we have the read request, and we also have ready. Ready is always here, but then read data valid will not go high. So here the instruction fetches, you can see it fetches, and then read data goes high when we get the data back into the CPU, and then it continues. Same happens with this instruction fetch. And then here it issues a write. The bus was ready, so it issued the write. But then you see we have a read request to this address, which, yeah, should be invalid. So this should be 4 for program ROM. This is always confusing when it's shifted like this, but I will just go ahead and pull up a calculator for it. But essentially 04, and we're going to shift this left twice, which should just be 1, 0. That seems a little off, doesn't it? So let's say 1 left shift 2 is 4. Yeah, that's correct. And then the 04 left shift 2 should be 1, 0. Yeah, that makes sense because that's where our program ROM is. And then this is where that invalid address was. Now, just to compare, by the way, if I change this to this, and we go ahead and regen the trace and reload this, we will see 2 things happen. We will see, first of all, this address will change. And then we'll also see that we get the data back, although it will probably take some cycles for that data to come back. So if we zoom out a little, I think it'll take a lot of cycles actually, because in fact, we should see that the bus isn't ready. Or no, I didn't rebuild the ROM, did I? Yeah, that's kind of annoying. Make test. Whoops. Like this. We should see, yeah, so what happened is the bus wasn't ready that cycle. It was ready the next cycle, which is kind of interesting. So that read got issued, but it's not coming back. I think the reason it's not coming back, by the way, this might also be a bug. I don't think it is, but this might be a bug. I think this actually waits for some simulated DDR initialization. What was I saying? So I think I need to extend how long my simulation runs. So this does this part here. I just happen to know where this is. Let's do a lot of cycles now. Okay, this actually seems wrong now, because this should work. What did I break? I wonder if this actually is wrong in the CPU. We might have found a bug, because this. What I think is happening here, this read request, this should be, let me dig in here. This should have a ready line here that should be low. So what happened here, kind of glad I get to show this, but not glad I have to deal with it. So what happens is we issue the write here, or the, yeah, I think it's the read actually. And I think we probably didn't see this first, because I think we only store into the ROM before it's ready. But in this case, we're doing a read. And what happens is we issue the read, but this bus says it's not ready during this cycle. And for some reason, when I do writes, this should just keep trying to assert that. I think it's this bus address that's not That's not correct. So something's happening here, which is either, let's see, what is the CPU trying to do? The CPU has the membus address. If we append this, we can see that the membus address is still here for the CPU. But we have this membus read request, and that stops after this cycle, which is interesting because what happens here is that we're trying to, we've put this address on the bus, which means that this ready signal here is going to reflect whatever the ready signal for that mapped unit is going to be, and that's the DDR3 interface. So if we're trying to do a read or a write, and we see that this isn't ready, what we should do is keep trying to assert that read. And you can see that it does do that. It says, okay, I tried to assert a read, it wasn't ready. But then here I tried to assert the read and it was ready. But it's not actually ready. This is just wrong. And it looks like also we're not trying to assert the read request anymore here. So I think that's wrong. I think somehow this memory state is not holding this read request as long as it should. But I think that works for writes because it must when it's initializing memory. In fact, if we remove this, which I think we have to do with these kind of comments, which I'll just do one here. If we remove this and make this, generate a new trace, what we should see is around the same time, actually a bit later, it's going to try to do a store into that memory. And it's just going to hold that the entire time until the simulated ROM or simulated DDR initialization is done. I don't remember how long I made that. But it should happen. Looks like that might not be happening though, which seems wrong to me. But you can see here, this is the ready for the DDR3 interface, so it might actually be okay. Because we don't see any reads or writes. We can also look at the membus. Let's see the system bus. Actually, I want to look at the xenowing system bus write request as well. And here we get some write requests, but it's after this is ready. So I think we might be okay here. I'm also going to look at some write requests coming out of here. The CPU. Yeah, you just go through, but it's after this init period. Now I know I saw this like working before, so like let's just change this to a store word. That'll make this even easier to see. And maybe I just straight up broke it. Entirely possible. I'm just a bit surprised. So this even changed these LEDs because I think it just does the store and then jumps into the stub anyway. So those LEDs should have changed like that. That's correct. But with this, we should see it should try to do a write, and it should just keep trying to do that until this becomes ready. Is what we should see. Nope. It does the write request. This says it's not ready, and then it just moves on. Okay, that's not good. That's not what should happen here. So to fix this, we need to go into the CPU. CPU.py. The issue here should be that the execute stage should, let's see. If we look at the CPU, we have execute. And execute should have a bus write request, for example, which happens in this cycle because then the memory one after that will happen the cycle later. That's correct. And the issue here seems to be that this bus write request here is only high for this cycle. This should actually stay high on the output of the mem stage. I know what the issue is. I know exactly what the issue is. So the output of the execute stage should issue these read or write requests. Here, these bus read or bus write requests. And actually, let's see. These should be high purely based on this instruction register here. Bus write request. And then bus read request as well. And it looks like, yeah, this is the issue. So what I do here is that this execute stage used to be folded with the mem stage. So I had it only actually issue these read or write requests if an enable signal was coming from the control logic. So that way if this had an old instruction in the pipeline and it was on a different stage, it wouldn't continue to assert a read or write when it knew it was done. This is a bug now because this should just be high coming out of this stage. And then on the mem stage, that's where that signal should actually be gated. So here it is, because there I take that in from the previous stage, and then I only put it out if that's enabled. If this memory stage is enabled. So that should be more correct. And then I actually wonder if this execute stage even needs an enable signal anymore. And I don't think it does. I think it was just used for that, but now that I've moved that to the memory stage for timing reasons, I think we can just get rid of this enable signal altogether. So I'm going to do that. And then we can go and simplify some other things. So for example, the control logic, we do have a register wait enable. I don't think we need an execute enable anymore. So I'm just going to get rid of that. And then in the very top level code in the CPU, we need to get rid of that as well. So this will be the memory state or execute stage no longer needs an enable. So we can get rid of that. It doesn't need any reset either because there's no registers. And then the control logic down here, also we get rid of execute enable. And I think that should fix the issue. I get a lot of these bits of signals are not used because the way I'm generating code, but this is totally fine. And now when we look at this, we should see that this one will stay high. And this one will only be high for the cycles where this is enabled, but because this bus will essentially stay not ready, this should work. There we go. There we go. So now this needs to wait until the memory is done initializing before it actually finishes that store. And then the load will do the same thing. So go ahead and cd-rom make, cd back here, make test. And we should see almost the same thing, except instead of write requests, we'll see read requests happening. But then we'll see the same kind of stalling, where it will continue to assert that until it gets a cycle where it asserted it and the ready signal was valid. And then it's going to continue down these different paths here. And you can see this bus write request and this request in from the execute stage just keep being asserted. And that's totally fine because that's just based on the input of the instruction register. So that's just going to stay like that. But again, that's just from the execute stage. So that doesn't actually matter. It's really just this one from the mem stage that's gated by the memory enable, the memory stage enable line that should stay high like that. So that should be good. So now when we refresh this, we'll see again almost the same thing, but this will be a read request that holds for this long before it moves on. Takes a minute to reload because it's a long trace. Doesn't have to be that long, actually, I think. Yeah, there we go. Same thing. Same read. And then here we have a bit of a delay because it takes a minute for the read to be asserted, which happens during this cycle. Because here we can see we have a cycle where it was ready and we assert the read, and then we stop asserting the read because we got that through. And then we stay in this pipeline stage in the CPU until, or actually we transition to the write back stage. Yeah, as soon as we assert this on the next cycle, we transition to the write back, and that will stay in that until we have a cycle where we get the read data valid. And then if we turn on something for the bus read data, which the mem doesn't have anymore because it doesn't read data. So, or I mean the mem should have. No, it shouldn't, because the write back is the one that reads the data. So bus read data will also be valid on that one particular cycle. And this will be whatever data that was, which is actually this one. In this case, I think it ends up being 0 in my simulator because it's just simulated memory, so it could be anything. But yeah, and then it continues. So this should work. Now we can remove this and feel much better about the CPU. So cool, we debugged an issue. Now that this works, I want to actually test the case that I want to break. So I'm going to do a quick commit. Now I'm also going to go back and turn this number back down because I don't think we need traces that are that long right now. Hopefully this is still long enough for that, which it should be. I think, maybe not. I don't think I generated the trace again, actually. Still good, I guess. I did rebuild it, so I guess that's fine. Okay, the other thing I want to do is I actually want to test this on the hardware. In particular, I want to run it through the compiler so we get a timing analysis. I suspect it'll just work. I'm not worried about that. But I just want to be sure before we move on and make the change that I actually want to make. And the change that I want to make again is going to be pretty trivial. It's just going to be making reads or writes to an invalid address just hang. Because the read will never be returned. I thought about if we made like a really simple GPU, like the simplest we could make, we could basically just have the CPU change registers on it over time, and we could synchronize with the GPU by having some kind of read port that will only return a value in sync with something else. So like at the end of VBlank or at the beginning of VBlank or HBlank, for example. And that'd be really similar to like what the Atari VCS does. It's got this register, which I think is at 02, where if you write or read to it, it holds the busy line for the bus, so instruction fetches can't happen until the beginning of the next scan line. And in this case, that wouldn't work because instruction fetches go to different memory, so it wouldn't be mapped to that peripheral anymore after it did that, so that wouldn't work. But a read to that, we would be able to do this by not returning the read until whenever we wanted to. But I don't think that's the kind of GPU I want to make, so don't think we'll do that, but fun to think about. And this is why I have invested so much effort into reloading ROM, a simulated setup, all that other stuff, because this compile takes a while, which rhymes. And I know no matter what, we'll see some timing errors inside the DDR controller, which is still really annoying to me. I tried actually regenerating the memory controller, and I had a bunch of errors. And I'm hoping that if I update Quartus and everything, and update all the different packages, that I could try that again, and it would just work. But it didn't last time I tried, so I'm hoping to defer that. That's a very frustrating thing, actually, because I kind of need that controller to interact with the memory. And I put in the values that it gave as an example in one of the labs from Intel's site. And yet, even in the test design that only has a very, very simple driver for the bus and the memory controller in it, and that's it, I still have timing errors. Oh well, it does seem to work anyway, so we'll go with it. The fast one always passes. Always get some kind of thing in here. It's always this stuff internally. Really dumb. In fact, this actually was a lot higher than I thought it was before, which that doesn't make me feel good. But we're running it anyway. There we go. Still seems to work. It reloads and everything. There isn't much else I can do with this other than actually change the ROM code. So, but what I want to do now is go and actually make that change. So what I want to happen is if we look at our system bus, which I think is in Python now, which is nice. I think I do all this memory mapping here. And so what I have is I have this dummy read valid thing. And essentially what this does is when you do a read to any address that doesn't recognize, it will just assert a dummy data valid signal on the way back, and you get whatever data is just on the bus. This way it wouldn't like stall or anything, but I think that's logic that I just want to remove. So the easy thing to do here is just get rid of this. Get rid of the dummy stuff. And what we can do is do what we did here, where we just map this to this program ROM in the default case, and then in the other cases, these signals will be muxed appropriately for these other interfaces here. Program ROM, the LED, UART transmitter, DDR memory. So nice and easy. In fact, I think that's all we have to do is let's just change that. So now if I go back here, do make test. And now it looks like it said here, new local added, dummy read data valid next. Probably because I still have this here for other addresses. And we don't care about that anymore. Good. And this should basically look the same. except of course it's a different pattern because I removed that stuff in the ROM with those dummy reads. But now if I go in here and I bring these back, we should be able to run this. If we change the ROM, then we'll see what we saw before. Like this. And then if we change this to 4K or, for example, 0, either one should work. In fact, let's do a random one. Like, let's do fade babe and just try to read from fade babe. Then this will just stall like this and just waits forever. Now a write, I think, will go through, but we just don't care. It'll just end up being ignored. In fact, it's undefined, so I think what it actually tries to do is it ends up writing to the ROM and to the program ROM, which that isn't even connected, so who cares? It's undefined. So that's the change I wanted to make. And that's really easy. Just removing code. And I'll also, just for good measure, build this. Cool. So that's another couple things that I wanted to do. And you'll notice that my memory map doesn't start at 0, and that's so null pointers will work. It starts at these addresses, which is fine. And then we're going to split up the system regs thing here. So what I want to do... Also, yeah, I was going to update the documentation here. I'll do that first, too. This isn't the most organized project ever, but it's definitely not the least either. So, yeah, we want to do interface and this GPU display and draw. I think we also want to put that here. UART transmitter. Interface. We want to do UART interface transmitter, and this UART interface, by the way, it should be transmitter interface. We can just do TX for this. That's fine. So the interface is different than the transmitter. So if we did this, we could do make doc. Or make, did that not work? Make docs, maybe? I don't remember. Just make worked, so I'll take it. And then in here, we can check our new topology here. And I guess before I had these on the same rank up here, so maybe I put that back. Yeah, I think I'll adjust that. Yes, this is more correct. This is what I want. And yes, this is bidirectional. I mean, all these are bidirectional in the sense that they're connected where one sends addresses to the other, so I think that's okay. Again, I want to adjust some things over here because this DDR3 arbiter might be correct, but I'm not sure. Hi, honey. I'm noticing the shit out of you. Love you. That's great. This is not the first time she's been out with the same friend she's out with and watched my stream, apparently. Which is great. So funny. So I think I actually want to remove some of this stuff to more accurately reflect what we have now rather than what we're going to have with the GPU. I think I want to do that actually. I'll do this. And then I still want to clarify the DDR3 thing here because I think this DDR3 arbiter is not correct. We have, if we, actually the RTL viewer is probably the easiest way to look at this. If we go to, also check my timing again, but we know this, we know what this is going to say. Same stuff, no problem. Tools, RTL viewer. So in this case, we have the system bus connects to this DDR3 interface. And that connects to the DDR3 controller. So the DDR3 arbiter here, this is actually DDR3 controller hooks up. Yeah, this is the full memory, and then this is the Avalon interface. So actually what we have here is this DDR3 is the DDR3 controller, which I'm just going to rename here. So this is still close to what we actually have, but not quite. This should look the same. But DDR3 arbiter is not correct. This is DDR3 interface. So this should be in rank with all those, which makes more sense. And then also this GPU display is not going to talk to the DDR3 interface. There's going to be another unit. So right now the closest this is going to be is the DDR3 controller, but there's going to need to be something in between there that we need to define, which is actually going to be an arbiter. It's just my point is that the DDR3 interface should actually be before this. And right now I just call this DDR3 controller, so I'm just going to keep calling it that, DDR3 controller, like this. I like having this stuff relatively up to date. Nice to stay organized. What I should actually do is have this generate SVG or something and then put that in the README. That'd probably be a better idea. Maybe have that update whenever I push or something. I really haven't spent any time on like making this project look nice from GitHub, but I figure I'll just do that sometime later because it's not, a lot of the architecture still in the air, so like why bother, in my head, why bother documenting too much of it? Whereas this is just a simple file, so I don't really care. It's not a lot of effort to do this. But what I expect is going to happen here is this GPU display is actually, the way it is currently is going to be GPU or display interface. And then I don't write a lot of dots, so I run the thing, or I look at the thing every time I change something. So the display interface is going to connect to something beneath it. And actually, if we wanted to order this correctly, this would be before this. Which I like to maintain this order. And this ordering isn't terribly important, but it's nice when it matches what's in my head. So we have the display interface, and then we're going to have this UART transmitter as well. In fact, let's go ahead and make all these kind of in the rows that they are. DDR3 interface. And then we have the UARTX and the DDR3 controller, but actually on this same kind of rank, we're going to have the display. I'll just call it display right now. And there's going to be more things that connects to eventually. But for right now, it's probably just going to be that. So the display interface goes to DDR3 controller. That's not actually true. It's going to be the display that goes to DDR3 controller. And then we need the display interface to also connect to the display. Why not just continue with this thing here, and then the display will be on this rank. And DDR controller should be underneath that. This is closer to what I'm thinking. Again, there needs to be another thing in between here that's actually going to be some kind of arbiter between these two things: the display interface from the CPU and the DDR3 interface, and the display from the CPU. So the DDR3 controller here, we're also going to make another one of these. That's going to be the DDR3. Actually, what I want is the DDR3 controller as is going to become the DDR3 arbiter. And then the DDR3 controller is beneath that again. And obviously I don't need to specify these when these are just on their own beneath here, but I kind of like having both there. So then down here, the DDR3 arbiter is going to connect to the DDR3 controller. So that should be how that works. I like having this kind of documentation as code because we can commit everything along with those changes. Although if this were a more graphical format, maybe that would make sense and be easier to modify. But this isn't too bad. So then the display interface is what you will use to interact with the display hardware, which is going to end up actually outputting pixels. That's the whole point of that. And then, yeah, this goes to the DDR3 controller via the arbiter, which has to manage traffic from both of these. Now, the way that happens should actually be basically identical to the system bus. In fact, instead of the DDR3 arbiter, we could call this the DDR3 bus, just like the system bus. And I kind of like that, actually. So we'll go ahead and replace arbiter with bus. think I like that idea. So in the same way that the system bus, or actually there's a crucial difference here in that this is kind of inverted. So the CPU has one sort of master and then several slaves. Whereas the DDR3 bus is going to be the opposite. It's going to have one slave and several masters. So it needs to do a little bit more complicated stuff with making sure that essentially if it decides that if we get like a read or write via the same or via both masters, we need to decide which one actually gets through and then tell the other one that the bus is busy, is essentially what we need to do. It's a bit more complicated than that because we also have to do reads. Whenever we get a read from either host, we would like to not just stall until the read comes back for this whole bus. That would be kind of the simplest thing to do. But what we would actually like to do is DDR3 harder bus. Chaotic evil indeed. What we'd like to do is we'd like to still issue the read and then have the other buses, whatever, still be able to issue reads and writes. And then whenever we get a data valid signal coming from the DDR3 controller through this, we maintain a FIFO of like which one of these devices issued reads. So whenever each one issues a read, we have a FIFO that says which one of these was the read that we issued. And then when we get the data valid back, we could pull off of that FIFO and then return the read to whatever interface. And we can actually do that in parallel. So like one of them can still be trying to interact, do reads and writes on the bus while we're returning reads that have been issued before. And as long as the systems here don't, like whenever they issue a read, they need to expect that a read's going to come back. And that ordering is going to be strong. So as long as they are not doing anything stupid in that sense, everything should work. I think that's how I want this to work. And then eventually, of course, we'll have the GPU interface as well, which is going to be in addition to this. And then this bus also has to arbitrate that. So we want a solution that works for 2 but generalizes to 3. See you later, Repnop. That's what we'll want eventually. But I think this altogether is good enough. But before we get to that, the display needs to be first interacting with the transmitter chip that's on my board. So that's kind of the first thing that we have to do, is interact with that. And there's actually a couple things here because the display, I actually want to add this, the DDR3 bus. I also want to add the ADV7513. This is that particular chip. This. Like that, I think is what I want. So the display is going to be interacting with this transmitter chip, and we want to make this path first. So we need to make this path, we need to start making this unit, and we need to do this. And the interface here is going to be an I2C bus, where this is the master and this is the slave. And again, I'm just going to expose some raw bits of that bus for reading and writing so that we can just implement the I2C interface on the CPU with our really quick reload functionality. So that should be really easy to do against the real hardware. And then later, if we want to move that part into hardware, we can, but we'll just start with software. And so we'll get it to essentially read and write the registers of the chip and be able to enable it, or even just read out register values just to double check that works nicely. Once that's done, we could hook it up to the bus. But before that, there's another step that I want to do. And that's just have a really basic pattern generator as part of the display hardware, because eventually we're going to need to do, we need to generate a valid video signal. And I would rather do that without the memory involved first. So we'll just see what our pixel timing needs to be like. We'll get it to generate again, a really simple kind of signal. And in fact, maybe what we can do is have two different kinds of signals and then be able to switch with the ROM. I think that could be kind of fun. The ROM could decide which one it would do. And then we also want to start doing things like the display. The CPU should be able to read if we're in VBlank, or it should be able to read like those kind of signals. So we need to sort of map a lot of that and get that basic data path going before we even worry about actually reading pixels from memory. Which once we have the timing and a lot of the other stuff ready here, then we can start focusing on that. And I think the arbitration that this is going to need to do is going to be relatively basic. I think the display is going to be the most timing critical thing that goes through this bus. And again, if we have an audio unit, that actually will also be timing critical and might go through that bus, but I might design it so that we don't actually have anything in this memory for that. Might just end up with like a really simple sound chip. And again, the graphics drawing hardware will also probably have its own memory for like a really small texture cache or something. But what was I saying? Yeah, so we really just need to arbitrate based on priorities. The display, when the display is trying to read memory here, and the display is only going to do reads, a read from display ends up, we need that to be the highest priority, because this is going to be timing critical in terms of getting the data from the DDR to the display, and it needs to happen when it happens. So we might end up with a little FIFO here too, as it's pulling out, and then it might just start issuing the reads early and then getting those back. So whenever that happens, we need to serve that first, and then second priority is going to be probably the drawing hardware, because we need that to be as fast as we can, and the CPU isn't going to be that useful for much anyway. It's a better use to block the CPU and give that like really good bandwidth, but of course it still needs to yield to the display. Because it's still the fastest way to get graphics on screen, and that's what we care about in this case. So the CPU will actually be the last thing that can touch this bus, and that will give us more motivation to do caches later on the CPU, which I still am not entirely sure I want to do. But that's a really good reason to do that, because we're going to have really reduced bandwidth for this once the GPU is actually drawing. And we're already going to have reduced bandwidth once the GPU is actually displaying. How much, I don't actually know. We kind of have to figure out the resolution, and then I have to look into what our pixel clock looks like and just kind of figure out all that timing before we start being able to really calculate that. And then I want to do a lot of tests when that works. I want to just start like dumping pixels into random positions in memory. Another thing, by the way, this display hardware is going to need is I want to map an address to where it's going to start reading from the DDR3 memory. Because I want that to be mappable anywhere. So essentially the way that we're going to do like a back buffer and front buffer is we're just going to allocate those buffers statically in the DDR3 memory. And then we're just going to pass different ones to the display. So that's also why we want to check if we're in VBlank or not, because then we can actually write to that register and we don't have to worry about video tearing. So yeah, pixel dumper. Fetch station. Yeah, we got to come up with a dumb name for that, definitely. So that's a lot of thoughts and not that much code. I'm getting kind of tired. It's a Friday night, so I might cut off the stream pretty soon here, just because I'm tired anyway, but at least just sharing these ideas is fun. I just kind of, to be honest, I don't really feel like digging into this much farther today, just because I want to relax. But I'm super happy with the progress we made today. I think this is awesome that we got this little blaster working. And even just, again, figuring out some of this stuff is really helpful. So I think I actually will go soon here. But I think I wanted to, did I compile this again? I don't remember. Put it on there just in case. But yeah, I'm really pleased with this. I think actually I made a ticket in this repo like last year. Yeah, here it is. First vertical plan. And you can see in here, Expand ROM reload tool to include file watching auto reload. It also says with manual trigger for when it fails. Don't need the manual trigger. Maybe we will later. I'm going to remove that because I don't think we need it. So that's something that I wanted a year ago and just now got. That's really nice. Cool. I love the names, you guys. Yeah, the next stages will be to start deciding how I want that mapping to work and then actually put that in the hardware. And start bit banging the ADV7513, that I2C interface. That's going to be the next stages. Extreme hardware accelerated GPU. I suspect it'll be a few weeks before we get to that. Maybe not. That would be awesome, but I suspect it will be. I think too, like the first commands that I want to have through the GPU are just like clearing, some really basic ones. We'll get there. But I'm excited. I think this will be really fun. So I'm going to head out. Thanks, guys, for hanging out, and I'll see you next time.